This is the efficiency expression for the transformer in terms of the primary parameters. The numerator V1 I1 cos phi1 will give you the power input to the transformer. Wi will be the iron loss. I1 square R01 will be the copper loss in the transformer. And the denominator again, it will give you the input to the transformer. Now this equation can be rewritten like this. If I divide the numerator with the denominator, I can write the equation as 1 minus Wi divided by V1 I1 cos phi1 minus I1 R01 divided by V1 cos phi1. What we have here is I1 square and we have I1. So 1 I1 cancels. I will be getting this equation. In this expression for efficiency, the variable is I1, which represents the current in the transformer. Under different load condition, the transformer will draw different current magnitudes from the supply. Therefore, I1 is variable. If I want to have maximum efficiency, we can take this expression for efficiency, which is represented by eta, and differentiate that with respect to the current I1 and equate this to 0. That is the condition for maximum efficiency. Okay. Now, when I differentiate this expression, differential of 1 is 0. And here I have Wi a constant value, V1 cos phi1, this is also constant. I have I1 in the denominator, so therefore differential of that will give you minus 1 upon I1 square. The next term, if I say I1 R01, I have here R01 divided by V1 cos phi1. Now since I am equating this expression to 0, minus into minus will give you plus. Therefore, I can also write this expression as R01 divided by V1 cos phi1 is equals to Wi divided by V1 cos phi1 I1 square. I have a common term in the denominator, that is V1 cos phi1 on both the sides. So for cancelling that and taking this I1 square to the numerator, I can write I1 square R01 is equals to Wi. So I have these two expressions as the losses, that is I1 square R01 will be the copper loss and Wi is the iron loss. So for the condition for maximum efficiency is when the copper loss is equals to iron loss, the efficiency will be maximum. Now this happens only at one load condition in a transformer. Now I will be just taking this expression, rewriting that. It is like this. I1 square R01 is equals to Wi. Let us write I1 square is equals to Wi divided by R01, or I1 is equals to square root of Wi R01. Now the transformer primary will have a full load current as I1 FL. That means when the transformer is fully loaded, the primary current will be equals to I1 FL. I will be multiplying this expression with I1 FL, okay, square root of Wi divided by I1 FL square R01. So this will not alter this expression, okay. Now in that expression, what I have, I1 FL, okay, multiplied by square root of iron loss Wi, and the denominator will be full load copper loss. So this gives you an expression for I1, that is the current at which the efficiency is maximum in terms of the full load current. That is I1FL. This will be a multiplying factor which is having no dimension, and usually for a transformer the iron losses will be lesser than the full load copper loss. Why? Because in the construction of the transformer itself, we will be taking care such that the iron loss will have two components, so that both the components will have minimum value. Okay, that means we will be taking care to minimize the iron loss in the construction of the transformer itself. Therefore, the ratio of what we have Wi divided by full load copper loss will be less than 1. So, the square root will result in a value much lesser than 1. So, that means I1 will be always less than I1FL, which says that the maximum efficiency will be occurring at a load condition much lesser than the full load condition. Now one more thing, if I multiply both sides of this equation with the terminal voltage V1, I will be getting V1 I1 is equals to V1 I1 FL multiplied by the ratio what you have Wi divided by WCU FL, that is the full load copper loss. Okay. Now you can see here, in this expression, I have V1 I1. This corresponds to the load in volt amperes, okay, measured from the primary side. And V1 I1 FL will give you the full load rating of the transformer. And of course, the square root of this ratio will give you a constant value. And as I told you that the square root value will be less than 1, you can see the rating at which the efficiency will be maximum will be lesser than the full load rating of the transformer.